Hey everyone, and welcome to this VLE on the Digital Intelligence Course Certificate class that my colleague Sarah Rispin Sedlak and I just finished teaching this term. My name is Akshay. I work for the Center for Computational Thinking, and this is the second version, the second time we've taught this class.
Hi, I'm Sarah Rispin Sedlak. I'm a lecturing fellow in the Duke Initiative for Science and Society, where I've been working with Akshay to develop this course. And what we're going to do today is give you, starting with, can we go to the slides? Great. We're going to provide an examination of the ethics of AI in healthcare, which we hope will provide a mirror, a view into how we conduct this course, and will also be of topical interest to many of you. Next slide. And the next slide. Okay, so one of the things that we start each semester with is talking about the sort of major forces in our world that are creating a potent mix of emerging technologies that is worth examining from an ethical and policy standpoint. And there are four forces that are conspiring. We have the digitization of experience, which definitely extends to healthcare. We see computing power, a great growth in computing power. We see incredible cloud storage, and we see advancements in machine learning and AI. And AI is, as anyone will tell you, incredibly data hungry. So that brings us to what are the sources for data to use in AI in healthcare. There are 5 major buckets. The first are electronic health records. You might be surprised to know that in the US, we've only had largely digitized electronic health records since around 2011, 2012. It has to do with legislation passed under the Obama administration. So this is a relatively new development. The next bucket we have is high resolution medical imaging. As medical imaging becomes more advanced and more computerized, this creates incredibly data rich images that AI can process. The next are biosensors, all sorts of sensors that can digitize what's going on in our bodies and feed it directly into computers. The fourth is genetic and genomic information, which is, of course, a rich and increasingly rich source of information. By this, I mean that we understand what genetic factors influence certain diseases and certain chronic health conditions, but we don't yet know all of what our genetic information is going to yield in the future. So once you give your genetic data to someone, that becomes a source for examination in the future. And finally, we have non-traditional healthcare data that comes from wearables and the Internet of Things. So I'll just give a couple examples of what I mean by that. Wearables might be your Apple Watch, your Fitbit, which can pick up on things like your heart rate, your blood pressure, that sort of thing. And the Internet of Things could be anything from what's happening inside your home, what's happening on your computer, and what's happening in your car. So increasingly in the healthcare space, people are interested in harvesting data from, for instance, how somebody drives. There are people who are looking into whether you can determine whether someone is experiencing the early stages of Alzheimer's because of changes in the way that they're using the pedals in their car. And that is now digitized, and that is now being recorded. Similarly, there are people who are looking to see whether people are sliding into depression because of the patterns of use on their computer keyboards, right? So that opens up a new can of worms that is not protected by traditional health data regulation. Next slide, please. This is the exciting part. The uses for AI in healthcare. There are sort of 5 major buckets again. The first and most exciting to most healthcare practitioners or is patient diagnosis, right? This potentially gives doctors the tools to see around the next corner. If you can look at masses of data and figure out from, say, somebody's electronic health record whether they are likely to develop a dangerous condition, if they are likely to develop diabetic retinopathy, or they are going to potentially have a schizophrenic break, that opens up an additional realm of options for doctors seeking to head off the worst health outcomes. The second is interpretation of images. There is, because AI, as I said before, is data hungry, which with these digitized, incredibly rich, data-rich images, there's a lot that can be done potentially, and there are a lot of people piling into the space to use AI or to harness AI to discern patterns in images that human beings can't discern themselves. So again, either say looking at images of, this could be looking at large numbers of images of brains to see signatures that we might not see, but that the AI can discern that represent, say, schizophrenia. Or this could be really, really good examination of one single patient's scan, say a scan of their breast to see if they have developed a cancerous lesion. The third is selection of treatment in acute care settings. So here the key is speed, right? If you're using biosensors, if you're using sensors on the patient's body that are continually feeding information into a computer, then there's potential for AI to recognize and suggest treatment faster than the human beings in the acute care setting might be able to recognize and suggest that treatment. The fourth is risk assessment and stratification. So that gets into the realm of patient health management. There's a great example of this at Duke Hospital, where they've pioneered looking at assessing, I believe it's 54,000 patient records a month to see whether those patients are at risk of rehospitalization, of being readmitted to the hospital. This is the type of thing that would be far too labor intensive for human beings to do, but that AI can do in much less time. And the final that I've hinted at already, talking about schizophrenia and brain scans, is pattern recognition in medical research. So AI is excellent at discerning patterns and potentially discerning patterns that we ourselves would not recognize. And so people are trying to, are letting AI loose, so to speak, on sources of data around patients and individuals with certain medical conditions to see if the AI can pick up on patterns indicating those medical conditions that humans would not themselves. Next slide. So with all of this potential comes certain risks. There are sort of 5 major sets of risks associated with AI in healthcare. Today, we're going to just preview 3 of them. We're going to look at bias, the need for fairness and the risk of bias, the problems around providing sufficient transparency and explainability about AI in healthcare, and the potential for privacy harms. There are also concerns about deploying AI that is not valid or correct, coming to good results. And there are also certain concerns around informed consent, having to do with treating patients essentially with AI, with computers, and using their data without full informed consent. But that's outside of the scope of today's presentation. Next slide, please. So we're going to start with fairness and bias concerns. This is what we would do in class with our students. The first thing that we want to establish is what exactly is bias. And I've been using a definition from a Brookings Institution report that I find incredibly helpful. Outcomes that are systematically less favorable to individuals within a particular group where there is no relevant difference between groups that justifies those harms, right? So what would that look like in the healthcare setting? That might look like failing to recognize that African American patients are in need of a certain level of healthcare because you've trained your AI model to look for people who have received a great deal of healthcare in the past as indicating that they need further help, right? That there's one such example. It's not AI, it's an algorithm, but there's been one such example in the past. Another example might be, and we'll treat this again later in this presentation, training AI to recognize dermatological conditions, but failing to train that AI to adequately recognize how dermatological conditions present in people with darker skin. Both you can see would result in outcomes that are systematically less favorable to African American or darker skinned individuals in the medical context. There are three major ways that these harms arise. They can arise through the model design itself. When you're using AI, they can arise through the training data that you use to train the AI, and they can arise through the inputs. And by that, I mean, if you train a model up, you design a model fully, you train it up fully, and then you turn it on individuals, and it has to then go and seek certain inputs to start to understand who this individual is and how they do and do not fit the model. That if the inputs that the algorithm or the AI relies on for sort of scoping out that individual may reflect historical bias, then that can result in a biased algorithm or a biased AI model. And what are the effects of this? In the healthcare setting, the major effects of this are denial of beneficial care and systematic underserving or misserving of certain populations. So from a healthcare perspective, from the perspective of doctors and healthcare providers who have ethical obligations to their patients, the effects of bias in AI when AI is deployed in the healthcare setting are of great concern. I'm going to turn to Akshay now, who will speak more to the technical reasons that bias can arise.
Great. Thanks, Sarah. Next slide, please. So various frameworks have been proposed to classify different kinds of biases. A comprehensive account of the different types of AI-associated biases is provided by Suresh and Gutag. Importantly, they highlight where in the machine learning lifecycle these biases can emerge. Broadly, these biases are associated with the data generation phase, which you can see at the top of the figure here, or the model building and implementation phases at the bottom of the figure. And this figure shows the various stages of the machine learning life cycle, including data generation, model training, and model deployment. And importantly, also indicates where different kinds of biases can creep into this life cycle. Next slide, please. So for a concrete example of the real harms of bias, we can take a look at this figure from the Gender Shades paper, which was a very significant publication by Joy Boal-Amwini and Timnit Gebru. And they evaluated the performance of a few systems. and made the disturbing observation that while the maximum error rate for lighter skinned males was less than 1%, this error rate rose substantially to, I think, around 35% for darker skinned females, making them by far the most misclassified group. And this figure here shows the gender classification confidence scores of the IBM system, which was one of the systems that they tested. And so the results here show that these confidence scores are close to 1, meaning highly confident, for lighter skinned males and females, but range from around 0.75 to 1 for darker skinned females. And the authors point to using more inclusive training data sets and the requirement to report accuracy for subgroups as potential solutions. Next slide, please. So, a recent paper in the journal Nature demonstrated the amazing potential of AI to accurately classify skin cancers using images of skin lesions as input. The authors make the important point that these models could be deployed on smartphones, meaning that they could provide a low cost alternative to millions of people who otherwise wouldn't have access or couldn't afford the services of a dermatologist. However, a review published late last year in the Lancet's Digital Health Journal that examined 21 publicly available skin image datasets found a significant underrepresentation of darker skin types. And this is potentially dangerous because, as in the gender shades example on the previous slide, models trained on these data are likely to underperform when presented with images of darker skin. Next slide, please. So this is a quote from a paper, again, by Gebru and colleagues, that highlights two important potential sources of bias. One is a mismatch between the training data and real-world test data. And the second is unwanted societal biases that are often baked into the training data. Next slide, please. So there are a few ways in which we can address bias. One of the ways in which, the first way in which we can do this is, as mentioned previously, is to attempt to use training sets that are more balanced and representative of the uh, test population. And also to detect and correct any biases that might be present in the training data. The second way in which bias can be addressed is to involve a diverse set of stakeholders throughout the various stages of the machine learning lifecycle. And this is oftentimes ignored, and it's unfortunately, frequently it's the case that the machine learning engineers are the only people who are really involved in this process, and it's only after the fact that people appreciate the potential harmful side effects that these models can have. A third way in which bias can be evaluated is to um, uh, evaluate the how like the potential harmful effects of using proxies for historical bias. So an example of this could be, and oftentimes proxies are used because it's difficult to measure the thing you actually want to measure. So an example of a proxy that is used for of a proxy is using the number of arrests as a proxy for risky behavior. And unfortunately, as we know, different regions are policed to different extents. So the number of arrests isn't necessarily a good metric or predictor of risky behavior or crime. Um, a third way to address bias um, is to ensure that, in addition to providing an overall metric of your model's performance, it's critical to also evaluate the performance of your model across all important subgroups. So this was something that Bolamwini and Gebru did in their gender shades paper, where they they assessed the performance of their model across gender and um, different skin types. And the final way, a final way in this case to address bias, is to allow for the continual evaluation auditing of the models. Next slide, please. So those are 5 ways in which we can address bias, and they, while all sensible, can require a lot of effort. One simple but really effective way to uh, address bias, or actually to combat the harmful effects of bias, is to, in the first place, identify it. And to do that, there was a paper by Bender and Friedman that proposed the development of these things that they called data statements. And we can think of data statements as being kind of like a nutrition label for data. And these nutrition labels, they make salient features of the data set, like its demographic composition, obvious. And here are some quotes from this paper that describe what data statements are and why they're needed. One of the quotes that I'll read out is that data statements are particularly well suited to mitigate forms of emergent and pre-existing bias. Another quote from this paper that I find really important is the final one here, that the widespread uptake of data statements positions the NLP community to document the degree to which it leaves out certain language groups and empower itself to systematically broaden the data catalog. While this last point specifically addresses the natural language processing community, this is important and useful advice for the AI community as a whole, because it can make evident systematic biases that exist across data sets that are used by various groups. Next slide, please. And I will now hand it off to Sarah.
Okay, so this brings us to the second sort of ethical concern that we're going to address today and that we generally put front and center for our students, which is transparency or explainability, or more truly lack of transparency and lack of explainability with respect to AI. What do we mean by this? There are two types of transparency we're talking about. Transparency about the use of AI in the first place, and explanations about how the AI works. Sometimes people may not want to disclose that they're using AI, and we urge that this is in order to sort of honor obligations around informed consent, especially in the medical context, that you should be transparent that you're using it. And you also, this is important both to the patients and to the healthcare providers who are deploying it. They want to understand how it works. Why do you want to understand how it works? Well, it's essential to accuracy and it's essential to trust, right? It's essential for doctors to be able to assess whether an AI application is giving a good piece of advice, or whether it is just sort of malfunctioning. So a great example that we use is one of the earlier prototypes of using AI to evaluate EHRs in the health context was a project called Deep Patient at Mount Sinai. And they found that it was extraordinarily good at predicting certain hard to predict health conditions on the basis of examinations of people's electronic health records. And of course, those health records include doctor's notes, they include scans, they include medication histories. They include all sorts of past diagnoses, blood test results over time, that sort of thing. And it was predicting certain health conditions, if they found out eventually, on the basis of the label on the MRI scans. Why was the AI learning that the label on the MRI scan worked or indicated likelihood of developing certain health conditions? Well, because Mount Sinai was looking at two hospitals within its system, one in Manhattan and one in an outer borough. And the AI discerned that the people living in Manhattan who tended to have higher incomes were less likely to develop certain conditions, and the people living in the outer borough were more likely to develop certain conditions. Well, that might have worked in this particular context, but what if they switch the machines? Or what if you try and deploy deep patient in Illinois or California, where the Siemens machine is in one place and the GE machine is in another, right? That's a confounding factor in the AI sort of going off script. So doctors really need to understand how the AI is coming to its decision in order to be able to evaluate whether it's accurate and in order to trust the results. And this, in the healthcare context, if you believe, which there's good reason to, that AI presents enormous potential benefits to the patient population, you want to see it deployed. You want to see the power of AI unleashed to create better health outcomes. But without accuracy and trust, doctors are not going to trust it, and therefore it will be underdeployed. Why is transparency and explainability often lacking? There are two major reasons. One is due to proprietary concerns. It's very hard to get intellectual property rights around algorithms and AI. So one response is to simply keep it quiet, to keep it under wraps, which then enables you to protect it as a trade secret. And the second, which Akshay will now get into, is the black box nature of advanced AI. As the discipline has developed, we simply are unable to tell exactly why certain AI models are coming to the decisions or discerning the patterns that they are. Next slide, please. So what are the solutions, broadly speaking? The first one, which addresses the problem of companies trying to keep AI algorithms as trade secrets, is to allow for third-party or governmental evaluation and auditing. And what do we mean by that? We mean that you can maintain your trade secret if you allow a third party to evaluate your AI model, and you give them all of the information about the AI model on a confidential basis. Then you're going to meet the threshold. You're still going to stay under the threshold for sort of blowing your trade secret and blowing that form of protection. The next two solutions are technical solutions. The most popular solution is what's known as explainable AI, which is often abbreviated as XAI. And the final solution is something that is espoused by Cynthia Rudin here at Duke, which is interpretable AI. Very briefly, explainable AI tends to sort of append an algorithm to your model to explain and to find proxies for what the AI was looking at when it came to certain decisions or when it discerned certain patterns. And Cynthia Rudin finds that suboptimal, and what she espouses instead is interpretable AI, which is building the AI from the ground up so that it is sending out signals about exactly what it's looking at as it goes through the process. And I'm going to turn it back to Akshay, who can explain this more fully.
Thanks, Sarah. So let's now take a look at a few ways in which explainable AI or XAI has been used for computer vision. Next slide, please. So heat mapping is an umbrella term for a popular type of approach whose goal is to evaluate the contribution of different regions of an image to a final prediction. Heat mapping approaches include saliency maps, occlusion analysis, and layer-wise relevance propagation. Next slide, please. So here we can see examples of these heat maps. While the outputs of these different approaches aren't identical, they all attempt to determine the pixel-wise contributions to certain predictions. So take, for example, occlusion analysis for the last image, which is of a dog. The red squares indicate that the corresponding pixels, are contributing most to the model's prediction. And we see that this approach indicates that the pixels that correspond to the dog's face are contributing most to the model's prediction that this is an image of a dog. Next slide, please. So why do we need our models to provide explanations? For one thing, explanations can help reveal model defects. In this non-medical example, a model was trained to predict a person's age given a picture of their face. The model was initially trained on data from the famous ImageNet dataset. Using one of these heat mapping approaches, we see that the model has incorrectly learned to negatively correlate smiling with older age groups, as indicated by this blue color around the lips. And the blue color means negatively relevant. This is simply a result of the lack of representation of smiling older faces in the ImageNet dataset. Um, and however, retraining using a larger and more balanced data set, which in this case was the rebalanced IMDb wiki dataset, appears to fix this problem. Next slide, please. So researchers like Professor Cynthia Rudin, as Sarah mentioned, argue that post hoc explanations, like the ones we just discussed, don't do enough. Instead, we need to integrate explainability, or rather what she refers to as interpretability, into the model. And let's take a look at an example of this. So one attempt at building an interpretable model is described in the This Looks Like That paper. The authors were motivated to build a system that mimicked the approach a person would take to do something like try to classify this bird, which is a clay-colored sparrow. And meaning that they would focus on distinguishing parts of the bird that closely matched classic or prototypical parts for the given bird. So similarly, a doctor looking at an image of a suspected tumor would compare it to a prototypical image from a medical textbook. And they refer to this process as case-based reasoning, or this looks like that. And they built a model that automatically identifies these prototypes for a given collection of images, in this case of birds. And when the trained model is then presented with a test image, along with a prediction, it also highlights parts of the image, seen here in these yellow squares, that look like some of these prototypes. It also shows you the entire source images from which these prototypes were taken. And in this way, the model doesn't just give you a prediction, but also gives you an insight into its reasoning process. Next slide, please. So a more recent and medically relevant application of this kind of case-based reasoning is shown in this figure from a paper published last year in Nature Machine Intelligence, also by Professor Rudin's group. And this approach is called IABL, which stands for Interpretable AI Algorithm for Breast Lesions. The goal of this approach is to both predict if a lesion is benign or malignant, and to also provide an explanation for this prediction. The first part of this figure shows a typical uninterpretable approach that simply gives a prediction. The second approach that uses something called attention is similar to the heat mapping approaches we just took a look at. So in addition to giving a prediction, it also highlights which parts of the image contributed most to the given prediction. But it doesn't tell you anything more. Finally, the IAIABL model not only makes predictions and highlights regions of interest, it also tells you why it considers those reasons to be important. And so, in a sense, mimics a human radiologist. And for the last section of this presentation, I will hand it back to Sarah. Sorry, Sarah, I think you're muted.
This brings us to the third major ethical concern, which we will discuss today, which is privacy. So we could spend an entire semester just discussing what privacy is and why we value it. But suffice to say that it's especially valuable in the medical setting. Why? It's essential to gaining trust of patients, right? They're coming into the medical context and divulging to you either through what they say to you or what they allow you to pick up from examination, whether physical or through testing or scans of their body, divulging incredibly sensitive information. This information is capable of revealing especially sensitive or potentially damaging notions about a person. So, for instance, you could be talking about their propensity to develop a fatal disease later in life, whether they are transgender, whether they are suffering from psychotic delusions, that sort of thing. There's all sorts of incredibly sensitive conditions for which you seek care, and incredibly sensitive they're incredibly sensitive conditions or a sensitive status that will be revealed in the process of seeking care. And you must maintain the trust of your patients, of course, in order to induce patients to seek care in the first place, which is what we want them to do. If patients began to fear that their data was being sort of sucked up and used for massive research projects or evaluation by AI in such a way that was going to harm their privacy, was going to violate their privacy, then they would be more reluctant to seek care in the first place. But what is the problem here? With the digitization of all of this data, the ability to keep that information private is compromised. It's compromised by the ease of data sharing, and once data is shared, by the near impossibility of de-identification. So what do I mean by ease of data sharing? Going back to before the era when all of our health records were digitized, I think we're at something like 90% of our health records are contained in electronic health records now. Your most sensitive thoughts, conditions, what have you, might be simply written down on a piece of paper in a file in your doctor's file cabinet. You could feel fairly confident that that information wasn't going to travel very far. But now that it exists within databases that are maintained by third-party providers, databases that are possessed by and shared among large hospital systems, you are much less confident in the fact that your data is not going to travel very far. People try to give reassurances and say, of course, this data is going to be anonymized or de-identified, right? And that therefore we'll take your name off of it, we'll take your address off of it. This data won't be traced back to you. No one will ever know that you are the person with this potentially life-changing health condition or this sensitive status. But as Akshay explores with our students in our class each semester, it is nearly impossible to actually achieve that in practice, simply because of the way that data, uh, once you have enough data points about a person, becomes sort of a unique fingerprint of that person. So, what are the solutions to the privacy problem, broadly speaking? In the medical context, we actually have more solutions than we do in, say, the in the government context or in the context of social media or other companies in general commerce possessing our data. One notion that is especially promising is that of data fiduciaries. So, therefore, if you entrust your data to a hospital or a hospital system or a research organization, they can act as a fiduciary to you and to the data subjects, meaning that they have a set of obligations to safeguard the privacy interests of the data subjects. How can they do this? One way is to use centralized databases or data warehouses with gatekeepers. So that gatekeeper would be in the data fiduciary position. So I think the best example of this is a little beyond the health context, is New Zealand. New Zealand has decided to centralize all of the government data about its citizens in one place. And because they have a, sort of a more broadly accessible healthcare system than we do, and more robust social services, that includes a lot of sensitive information about individuals. Now, they feel that this data contributes to research, and that research in this data and use of an analysis of this data is in the public interest, right? Just as AI analysis of electronic health records and other patient data is potentially in the public interest. But what they do is they allow researchers to only go into that database for a limited purpose, right? They have to identify the purpose for which they're looking through the database ahead of time. They have to seek permission of the gatekeeper to go into it. They have to store the data that they extract in a certain place. They have to give representations about what they will and will not disclose about that data, etc. Right? So it essentially becomes, a pile of treasure kept in a vault that a curator or a museum guard or a bank guard lets them in to see and use, and then takes back before they leave. And the final option are federated data sharing or federated learning models. And I'm going to turn it back to Akshay to explain what those are.
So, federated learning is a fairly recent approach that was invented at Google, and it was designed to take advantage of the computational power of smartphones and tablets and the different kinds of data that they collect. So rather than collect data in a central repository that can be used to train various machine learning models, this approach offloads the model and the training onto the individual phones or tablets. Next slide, please. Oh, actually, I'm sorry, previous slide. So the process, the federated learning process, starts with a download of the current model with its various parameter values to multiple devices. And when I say current model, this could be a model that predicts the next word when you're sending a text message, or automatically, draws bounding boxes around faces of people. So uh, so the process begins with the download of this model, and the model then gets retrained using local data that are on these individual phones or tablets. So the model updates, but not the data, are then sent back to the cloud in an encrypted manner. And all these various uploads are averaged with the aim of improving the original model. So in this way, federated learning enables mobile devices to collaboratively learn a shared prediction model while keeping all the training data on device. And this approach has many advantages. Um, for one thing, since there is no need for the user's data to be shared with anyone else, federated learning provides a high degree of privacy protection. Second, given the incredible amount of data that is collected on all our devices, collecting and storing these data in a central repository would be prohibitively expensive in terms of computational power, time, and money. And finally, this approach enables the use of a wider variety of training data, resulting in models that are hopefully less biased. So an example of how this approach is used by Google itself is to improve the Google keyboard on Android devices. So when Gboard provides a suggestion, the phone locally records information about the current context and whether a user clicked the suggestion. And this information is used to retrain the query suggestion model, leading to improvements in the next iteration or the next version of this model. Next slide, please. Another setting where training data are generated in geographically different regions and where privacy protection is absolutely critical is healthcare research. An especially pertinent recent application of federated learning within the healthcare setting was a global study um, that that sought to train a model that could use medical data like chest X-rays to predict the future oxygen requirements of symptomatic COVID-19 patients. Here's a map that shows various countries and centers from which the training data were collected. The untrained model was sent to each of these locations and separately trained at each location using the local training data. Model weight updates were shared in a secure way with a central server, and they were all combined. So in this way, the model could be trained using all available training data without the need to share the actual data. The updated model, in turn, was again sent to each individual location to be retrained. And this process, this kind of back and forth training process, is conceptually similar to the repeated rounds of training that are used in conventional machine or deep learning. And this back and forth process was repeated until the model converged at some loss function minimum. Again, just like you see in kind of conventional machine or deep learning. And what the authors of this study found was that the final model achieved a very high performance with a high true positive rate and a low false positive rate. The second figure shows the wide distribution of training data images collected at different sites. And it's clear from this plot that some locations were only able to collect a handful of images. And the authors make the important point that a site with a relatively small data set would typically have two options: either training locally with its own data or use a pre-trained model that was trained on a larger data set. And the problem with the former approach is that these large deep learning models are data hungry. So there would likely be insufficient training data to produce a useful model. And the problem with using a pre-trained model is the heterogeneous nature of medical data that is spread across the world. Federated learning addresses both these problems. Data from smaller sites, in a sense, get pooled with data from other sources. So the model ends up receiving a sufficient amount of training data, and federated learning has the ability to capture more diversity than local training. And this thereby mitigates the bias problem that would be present or that might be present in models that have been trained on a more homogeneous population. And I will hand it over to Sarah to conclude this presentation.
Thank you, Akshay. So what are the takeaways we'd like you to take away today? The first is that, as with other emerging technologies, the use of AI in healthcare carries both benefits and risks. So we should neither be so in love with the benefits and the potential that we ignore those risks and the risk of imposing harm on the data subjects and the patients that are involved in the process with us, nor should we be so alarmed at the risks that we shy away from working to achieve those benefits. These risks can be tackled with both procedural and technological solutions, right? What do we mean by that? Take bias, right? Procedurally, we're advocating that you involve diverse stakeholders at all stages of the process, during model building, when you're selecting the inputs that you're going to use, when you're evaluating how well the model works, when you're auditing it after the fact. And we advocate solutions such as working to de-bias your training data sets, working to make your training data sets more representative. And in almost every context that we apply this lens, to almost every emerging tech application that we examine in our class, you find that it can be tackled with both procedural and technological solutions, that both should be employed. So what is our approach? You saw our approach today, to help our students and our audiences understand the scope of the risks and the benefits, and how to responsibly address the risks to help society achieve the benefits. And what we did today, examining this in the healthcare context, is both helpful to understanding the specifics of this case and thinking about how to analyze emerging tech in other contexts. So I'm sure you could look at other examples of where AI might be used. Let's take, for example, AI to power self-driving vehicles, right? What you would want to do in that case is first look at the benefits. Why do we want self-driving vehicles? What do we stand to gain from this? And then you would want to look at what the risks are. The risks are that the vehicle may not be as good as human beings at discerning and avoiding harmful accidents. The risks are that you may lose a sense of agency and responsibility in the people who are deploying the cars that any human or almost every human driving a car would have, and so forth. And then once you have both of those categories of information firmly in mind, you can then proceed to think about how to ethically deploy that technology, right? So in this instance, some procedures that people make sure that are in place are having humans in the loop at all times when self-driving vehicles are deployed on the roads, trying to make sure that those humans aren't overboard, so that they actually do remain in control and can be the avoider of last resort, the person who will avoid an accident that maybe the AI model hasn't anticipated or isn't trained to cope with. And so in sum, we hope that if you came here today interested in AI in the healthcare context, you have a better map of both the potential of that technology and the risks associated with it and how to address those, and that you have a map in your head of how to turn that kind of thinking to a useful and responsible evaluation of other emerging technology.
Just look to see if there are any questions. It doesn't look like there are any. So I guess thank you for watching, and I hope you took something away from this talk.